We have two different ways to determine if figures are similar. One definition says that two figures are similar if the figures are equiangular. You can kind of see what this word means, right? It's got equi and angular, meaning the two shapes have equal angles, the same angles. To give you an example of what that means, do these shapes here have the same matching angles? No. Look, this one's 70, but this one's 80. So these two shapes are not equiangular. The other rule that has to be true, this fact has to be true as well as the equiangular thing, if they are to be similar, is that corresponding side lengths are in the same ratio. Corresponding means matching. So for example, 3 to 6, these are matching sides, right? 3 to 6 has been doubled, multiplied by 2. 6 to 12 has been doubled as well. 6 to 12 has been doubled, and 4 to 8 has been doubled. So these figures here, they match the first rule. Yes, they do not match the first rule. No, they are not equiangular, but they are in the same ratio. The rule says that both things need to be true. We'll come back to that after this second definition. This second definition says that another way of proving that things are similar, it's the same as this definition, is that one is an enlargement of the other. So you've scaled up everything in the same ratio. We're asked to determine whether these two shapes are similar, and we have already seen that they fail this first test. So they can't be similar because they have to pass both tests. So we can say the ratios match, but their figures are not equiangular. Therefore, they are not similar. The crucial thing here is we're providing a reason they're not equiangular, and therefore a conclusion. So therefore, because of this, they can't be similar. We can determine whether these shapes are similar, and there is something that makes this one trickier, isn't it? Why can't we look at whether these two shapes are equiangular? We've got this triangle here and this one here. Why can't I verify whether they have the same angles? Well, we're not given any angles. So that's going to make it harder to prove if they're similar or not similar. We might still be able to prove that they're not similar, maybe. Let's check this second thing. The corresponding side lengths are in the same ratio. Let's check the ratios. I'm going to check the ratio of the new shape, A dash, B dash, C dash, compared to the old shape, A, B, C. Let's look at this distance here. This distance is A dash to B dash. It's the distance between these 2 points. And I want to compare that to the matching length on the old shape, the original shape, which is AB. So this ratio, A dash, B dash, I can replace with 4, and AB I can replace with 2. Now I can figure that out. 4 divided by 2, which is 2. That makes sense. From 2 to 4, it is doubled. That's why it's 2. Now let's look at another one. Let's look at A dash, C dash, and AC. A dash, C dash is this one here. And AC is this one here. Notice that I'm trying to be consistent. I put the big shape on the top both times. It's important to be consistent. Anyway, A dash, C dash is 10, divided by AC is 4. So I replace A dash, C dash with 10 and AC with 4. 10 divided by 4 is the same as 5 divided by 2, which is 2.5. Are these ratios the same? No. So because it fails this test, it can't possibly be similar. Even if I don't know whether they're equiangular, I know they can't be similar. Because to be similar, both these things need to be true. The side lengths are not in the same ratio, therefore not similar. Boom! Mic drop. Done.